Fractals is a term that we don't usually hear on a daily basis. Yet, unknowingly, we encounter fractals every day from the food we eat, like cauliflowers and broccoli, to the plants inside or outside our homes, like ferns and the branches of trees. Inside our bodies, such as systems of blood vessels and their nerve dendrites, and those beyond us, like the clouds and the distribution of galaxies in the universe. These are a few of the many fractals there is. The term fractal was coined by the American French Polish mathematician named Benoit Mandelbrot. In 1975, he defined a fractal as a rough or fragmented geometric shape that can be split into parts, each of which is a reduced copy of the whole. Fractals have three distinct characteristics: self-similarity, iteration and recursion, and finally, fractal dimension. The first characteristic of fractals is self-similarity. Fractals are complex geometric figures that are formed by repeating a relatively simple pattern. This means that no matter which part of the fractal we focus on, it will always resemble the whole fractal. The only difference they have are in terms of scale. Another distinct characteristic of fractals is iteration and recursion. The word iteration means repeating the same process over and over again, while recursion means applying the same process to the succeeding results. Fractals get their characteristic of self-similarity by following and repeatedly applying a rule or equation to generate new sets of values. With our new results, we apply the same rule or equation and continue doing the same process each time we get new values. One of the most interesting characteristics of fractals is their fractal dimensions. Fractal dimension describes the space that fractals take up and what dimension they are in. Contrary to our known dimensions, fractals lie between two different dimensions. Their dimension values are in non-integer numbers. In order to compute for a fractal's dimension, we use the scaling dimension relation formula C is equal to S raised to D, where C is the number of copies of the original shape needed, S is the scaling factor, and D is the dimension. We then apply our knowledge on the laws of logarithms to isolate the variable D. We are then left with the formula log C over log S is equal to D. We can now use this formula to directly solve for the fractal's dimension. Here, we have an example of a fractal called the Sierpinski carpet. As you can see on the clip, each time we zoom in, we see that each part of the fractal resembles the whole. This is a proof that this fractal is self-similar. Now, we have two copies of the Sierpinski carpet, a smaller one on the left with a scale of 1 and the larger one next to it with a scale of 3, since it is thrice as tall and thrice as wide as the smaller one. We can solve for the fractal dimension of the bigger copy by first counting the number of smaller copies it contains. We can see that there are 8 copies. Now that we have all the necessary information, we can use the scaling dimension relation formula and solve for the fractal dimension. As you can see on the computation on the right, the fractal dimension of the Sierpinski carpet is 1.8928. Fractals can be generated using different techniques as well as with the aid of computer programs. In this part, we will be learning about two of the many techniques used for generating fractals, namely the L systems and the iterated function system. The L systems, or the Linden-Meyer systems, was created by a Hungarian biologist and botanist named Aristide Linden-Meyer to describe the branching patterns of plants as well as the growth of simple multicellular organisms. Later on, L systems were used to generate self-similar fractals because of the nature of its rules. L systems have four components: the variables, which are symbols that will be replaced later on using the production rules. Variables can be any of the letters included in the English alphabet. Second, we have the constants, which, unlike the variables, do not get replaced by the production rules. Common constants are the addition and the subtraction signs. Next, we have the axioms. This is our starting point. Lastly, we have the rules, which defines how each iteration will be formed. The simplest example of the L systems is the one that Lyndon Mayer used to model the growth of algae. On the left side of the screen, you can see the components of the L system for this example. As stated on the components, our variables are a and b. The starting point or axiom is the variable a. On our first iteration, which we will call generation 1, we have to follow the rule and replace a with a and b. For our second generation, we will replace a just like how we did previously, and then replace our b with a. For our third generation, we replace all our a's with a and b, and replace all our b's with a. We continue doing this for the succeeding generations. After 5 generations, this is what the algae growth model looks like. Here, we have the L system components of the fractal called the Coke Island. As you can see, we have the variable f, the constant plus, which means turn right 90 degrees, and minus for turn left 90 degrees. Our generation 0 is our axiom, which is f plus f plus f plus f. For our first generation, we replace each f in generation 0 with the replacement rule written on the left. We will have this resulting string. For our second generation, just like what we did previously, we replace all the f's with our replacement rule, but this time, the f's that we will be replacing are those written in the first generation. We will now have this long string. We can continue generating more generations, but as you can see, the resulting string gets significantly longer in each generation. We now proceed to drawing each generation in the previous slide. Our generation 0 is f plus f plus f plus f. F means draw a line forward. Plus f means turn right 90 degrees and then draw a line forward. We do this 2 more times and end up with this resulting image for our generation 0. As seen in the previous slide, we have the string for generation 1. First, we draw a straight line for f, and then turn right 90 degrees and draw a line for plus f. Next, we turn left and draw a line for minus f, then turn left and draw 2 lines for minus ff. If we continue doing this, we will have this resulting image. Here is our string for generation 2. If we draw this, we will have this resulting image. Another fractal generating technique is the iterated function system or IFS. The iterated function system is a technique of generating self-similar fractals by repeated substitution. A subtype of the iterated function system is the multiple reduction copy machine algorithms, where we continuously reduce and even replace parts of our original image. A great example of this is the Cantor set. An example of a fractal that can be generated using the multiple reduction copy machine algorithm under IFS is the Cantor set. To generate a Cantor set, we first need a line. Here, we have a line in generation 0 whose length is 24 centimeters. To move on to our first generation, we copy this line and locate its middle third. The middle third is from 8 centimeters to 16 centimeters. We then take off this part of the line. We now have 2 lines whose lengths are 8 centimeters in generation 1. We copy these lines, locate and cut off the middle third of each line for generation 2. We continue doing this for each line we get in each generation. After 5 iterations, this is what the Cantor set looks like. This is a fractal I made using PowerPoint. It's a Christmas tree made entirely of the triangle shape in different scales. As you can see, every time we zoom in, it looks exactly like the whole fractal but in a smaller scale.